Okay guys, let's take a look at today's lesson. So what we're looking at today is a different technique on finding volume. And we need this technique, and you're probably thinking, no we don't, no we don't. Yes, we do. We need this technique, and let me explain why. When we are working with discs and washers, we really don't get to choose which variable that we're going to be using, right? If we're rotating around a horizontal axis, we have to use x's. We don't get to pick. If we're rotating around a vertical axis, we have to use y's. We do not get to choose. So let's envision a time where, let's say we have an equation, that looks like this. Let's say we have, y equals 3x cubed plus 2x squared minus x plus 15. Let's say we have an equation like this, and that we are going to rotate this about a vertical axis. That has to be an x equal equation with y's in it, right? What do you think the chances of us being able to get that into an x equal equation with a bunch of y's? Like, it's not going to happen. It's not going to happen. So we need another technique. We need another technique to be able to use when we have a situation like this. This would be like, how would we even do that? How would we even solve for x? I have an x cubed, an x squared, and an x. What would that even look like? Why we don't want to have to go through any kind of scenario like that. So what we have is shells, which is exactly the opposite from disc and washers. Shells is if you are rotating about a horizontal axis, you have to use y's. And if you are rotating about a vertical axis, you have to use x's. That is really the benefit of this other technique, is really when we get into a situation where we really can't, like this, we really can't solve for x. That's not going to happen. Now, I will tell you on the AP test, they aren't going to give you anything where you have to use shells. Okay, and on Wednesday's test in here, I'm not going to give you anything where you have to use shells. You always would be able to use discs. We're going to test on this lesson in Unit 7. This lesson, the shells lesson, will be tested in Unit 7. So it is a very different kind of procedure, though. It doesn't calculate volume by, disc and a washer. There aren't two different versions of this formula. It does it completely differently. So after you've had 3 days of disc and washers, I hope that you have that concept firmly implanted, so that because typically what would happen when I would just do 1 day disc and washers and 1 day shells, students would get them all confused because, they just would. So we are clear on disc and washers, right? We're integrating a circle, pi r squared. It's either a disc or a washer. All right. So let's talk about how this is formatted. So let's write down the formulas first. If we are going to be doing volume about a horizontal axis, our formula is going to be 2 pi integral a to b of r of y times h of y dy. Now we're going to talk about what those functions r and h are in just a moment. So 2 pi integral a to b, the reason that we're in y's is because it's a horizontal axis. Okay? So when we have a vertical axis, we're going to be in x's. So this is going to be 2 pi integral a to b r of x, h of x, dx. So those are our formulas. Notice how different they are. This uses 2 pi, not pi. So you can see where some students may get confused, and they may try to make a disc and washer with a 2 pi. But it's not, right? It's pi r squared. This is different. This is 2 pi times the radius times the height. Let's talk about what each of those things are. R of x or r of y, whichever variable we're in, is the distance from the axis of rotation to the figure. So I have some pictures right here for us to look and see what does that mean. If this is my axis of rotation, r is going to be measured from the axis inside the figure. If this is my axis of rotation, again, r is measured from the axis inside the figure. It doesn't matter how far you go into the figure, anywhere in the figure. And usually R is what students get most confused with. And I'm going to do some examples, explain it in detail. But R is usually where they get tripped up. Students usually get tripped up. H is the height. The height of the figure is the height that's parallel to the axis of rotation. So in this particular, when this is my axis of rotation, it's vertical, this is my height right here. That's my height. And for height, we can always do big minus little. It's always going to work. Big minus little for height. So height usually does not trouble students. Usually. Okay, height is just big minus little. Over here, so you can see this is a vertical axis. So we'd be with x's, right? And so this would be big minus little. Tall minus the small one. Here, this is a horizontal axis. So we would be with y's. And this height right here is parallel to the axis of rotation, would be big minus little, right? Big would be the biggest x over to small. So let me just let you absorb that for just a minute. Okay, so that's what R and H are. Okay, this is just, I picked this picture up somewhere on the internet. It's just a demonstration. It's this concentric cylinder. The cylinders are shells. Which is where this comes from. Okay. All right, so let's jump into some examples. So the first one asks us to set up an integral expression that can be used to find the volume when the region is bounded by. So we have x squared plus 1 and y equals 0. And we're going to, the first one, we're going to rotate about the y-axis. We're going to be using shells. Okay, so here's our parent parabola shifted up 1. Let's see, it goes 1 and y equals 0 is this part right here. And we're bound by from 0 to 2. So we're bound right here at 2. So let's see, we start here. So it's a parent parabola here, and then over 1, up 1, 2, 1, 2, 3. Okay, something like that. Okay, so this is the figure that we're looking at. This is what's bound. We're bound on all these sides right here. Okay, we're going from 0 to 2, y equals 0, so 0 to 2, x bounds. Here's y equals 0, and there's my function. That's what we're rotating. And we're rotating about the y-axis. Okay. So let's put on here R and H. Okay, R is measured from the axis of rotation into the figure. That's R. H is measured from one end of the figure to the other, and it's parallel to the axis of rotation. That's H. Okay. So R is typically where we have the most trouble. I want to talk about R. R is this distance. And it sounds really complicated, but if you can really kind of go back with me to when you first started graphing, you know, on an XY plane, we know this distance measurement is X. Right? If we said x is 1, we would go from here to here, wouldn't we? That'd be x of 1. If x was 2, we'd go from here to here. R, when we're rotating about the y-axis, is just x. It's just x. It's this distance measurement. So measuring from here to here is just x. R is going to be x. H is going to be big minus little. Right, and so it would be the function, which is y squared plus 1 minus 0. So it's just x squared plus 1 minus 0. So it's just x squared plus 1. So I'm going to pause there for just a second. Are we okay with how we found R and H? So now we're just going to put it in the formula. Right, the formula is 2 pi integral R times H. I mean, that's the formula. So 2 pi integral from, these are x's, vertical axis, we have to have x's. My x bounds are 0 to 2. r times h, so x times x squared plus 1 dx. And that's my formula that I would put into my calculator. Hopefully you all have our calculators with us. We are still working with calculators on this unit. So we put that in our calculator and we get 37.699. Okay, so that is the volume of that figure. Alright, so we're going to use the same figure, but we're going to rotate around a different axis. This time we're going to rotate about the axis x equals -1. So we're out here at -1. That's what we're rotating around. We still have this figure. We've already drawn it once, so that's it right there. Okay. So r is the distance from the axis of rotation inside the figure. That's r. H is from the top of the figure to the bottom of the figure and measured parallel to the axis of rotation. Parallel. Okay. So let's figure out what r and h are. So r, again, that's usually the one that gives students the most trouble. Let's talk about r. From the y-axis out, we just talked about that being x. Right? If I want to know any spot in here, I would just, that's the distance x. Right? From the y, right from here to here is x. But I need more than that. Right? I need one whole unit more than that. So r is going to be x plus 1. So r is x plus 1. H is still big minus little. You know, the function minus 0. So x is still, h is still x squared plus 1. Okay, so let's write our formula. So 2 pi integral. Now here's what was confusing students earlier today. The bounds are the bounds of the figure. They have nothing to do with r. 0. The bounds that I use here are bounds from the figure. The figure goes from 0 to 2. Just because r happens to be over there at -1 does not mean that changes my bounds. That's how this formula deals with holes. Right? We had in disc and washers, we had a different formula if it had a hole. This formula doesn't need a different formula because the way it deals with holes is it pretty much ignores them. Right? The holes are included in r. That extra distance is included in r. And so instead, what we want is the way it deals with it, it binds it from 1 to 2. Okay, from 0 to 2, from 0 to 2. So the figure is how we get these lower bound and upper bound. Okay, so it's that 2 pi r times h, so x plus 1 times x squared plus 1 dx. We put that in our calculator and we get 67.021. Okay. Is that okay so far? Y'all are looking at me like you've lost your mind. No, it's going to be okay. It'll be fine. Okay? So the next one, we want to have another example. Here we have y equals square root of x, y equals 0, and x equals 4. So let's draw that. So we're going from, square root of x to an x of 4. We know that that's at 2. Okay, and we're stopped at x equals 4. This stops us. Y equals 0 is this part right here, so we're just bound in right here and at 4. Okay, so that's the figure that we're rotating. Alright, so this one wants us to rotate it about the axis x equals 7. So 4, 5, 6, 7. So we're going to rotate about this axis. It's a vertical axis, so we need x's. Vertical axis, we need x's and x bounds. So, okay. So let's work on R and H. So R is the distance from the axis of rotation into the figure. That's R. H is measured parallel to the axis of rotation. This is H. Okay, so R is a little bit crazy. Let's look at it. This portion right here, I hope we have really in our minds, the portion from the y-axis over is x. And that's x. If I was rotating about the y-axis, R would just be x. Every time, always. If I'm rotating about the y-axis, R is x. No thinking needed. So if this is x, and I don't want x, I want this part over here. So I need to think about how could I get this part? What could I do? You know, and certainly R could be measured anywhere inside here. This is just one example, right? The R's, there's an infinite number of R's. So I need this part, not that part. So I would do 7, take away x, right? 7 would be this whole distance, and I want to take that part out. So R is going to be 7 minus x. Okay. Now H, again, big minus little, it's just the square root of x minus 0, so it's just square root of x. So let's write our formula. So we have 2 pi integral. Okay, again, we have weird stuff going over here, but our bounds doesn't matter. Our bounds are from 0, you know, where the figure is, 0 to 4. 0 to 4. And then it's R times H. So 7 minus x times square root of x dx. And we get 154.147. Okay. So we're using the same figure, and now we're going to rotate about the line y equals 5. Okay, that's going to be a little different. We still have that figure. Okay, the line y equals 5, 2, 3 is up here. That is a horizontal axis of rotation. What variable do we have to be in? Y's. We have to be in y's. See, again, the benefit of this technique is it reverses it, just in case that would be more helpful to us. So the first thing I need to do, I don't have x equal equations. I'm going to have to go over here specifically to this one and change that to an x equal equation. So let's see, that would be x equals y squared. Okay, so I have an x equal equation. Okay, so let's work on R and H. So R, I've probably said this at least 10 times, okay? R is measured from the axis of rotation inside the figure. That's R. H is measured from the top of the figure to the bottom of the figure, parallel to the axis of rotation. That's H. Okay. So we need to find an expression for R and H. Now we haven't done one yet on a horizontal axis, but it's really same concept. If I am going from the axis up, the x-axis up, that distance is y. Right, measured from the x-axis up is y. If I wanted to know what this height was right here, I would just put a 1 in there and I would get my height, right? That would be my y value. So this is y. Now, as it turns out, we're not rotating about the y-axis. If we were, the x-axis, if we were rotating about the x-axis, R would be y. But we're not. We're rotating up here. So we don't want y, the y part, right? We want 5, which is this whole space, take out y. So R is going to be 5 minus y. Now, just when we thought that the height was okay, this is a little weird, but let's think about it as big minus little. Okay, instead of trying to conceptualize it right now, let's just think big minus little. This is y's. So bigger would be farther right, where the x's are bigger. Where x is bigger, that would be bigger. So the farthest right over here is actually just a line at, what, 4. 4, big is 4, minus little, little is y squared. So big minus little would be 4 minus y squared. That's my height. Okay? So this time when we write our formula, I'm going to need y bounds, right, from 0 to 2. The figure, lowest y value in the figure is 0, the highest y value in the figure is 2. So let's write our formula. So 2 pi integral 0 to 2 of 5 minus y times 4 minus y squared dy. And when we do that, we get 142.419. Okay. Okay? All right, the very last example, what we're going to do is we're going to do the same example 2 different ways. We're going to do it with shells first, and then we're going to do it with a disc or washer. And it does not matter which technique you use. You should get the exact same answer. Okay, they're just 2 different techniques to do the exact same thing. So let's do shells first. So we want to rotate about the y-axis. And we have x squared and x to the 1/3. So I'm going to exaggerate the picture just so you can see a little bit better. It kind of goes like that, but again, that's exaggerated. They intersect at 1, 1 is where that intersection point is. 0, 0, and 1, 1 is where those intersect. Okay, so this is my axis. So let's calculate r and h. R is the distance from the axis of rotation inside the figure. That's r. H is the distance from the top of the figure to the bottom of the figure. That's h, measured parallel to the axis of rotation. So r, since I'm rotating about the y-axis, r is going to be x, period. I have some students, if this is shifted off, they're thinking they need to change r. No, r is going to be x. It has to do with the axis of rotation, not the location of the figure. Okay, r is the axis of rotation, not the location of the figure. So it's from the axis of rotation, so that is just x. H is going to be big minus little, right? Big minus little. And so this would be x to the 1/3 minus little, and little is the parabola. Okay, so let's write out our formula. So 2 pi integral, and they're x bounds, so 0 to 1 of r, which is x, times h, which is x to the 1/3 minus x squared dx. I work that out and I get 1.12199 or 1.122. That's with shells. Now we're going to do the very same thing, but we're going to do it with discs or washers. So again, I'm going to kind of exaggerate the drawing. That's 1, 1. We're rotating about the y-axis. Since we're rotating about the y-axis and we're using discs or washers, what variable do we have to use? Y's. We have to use y's. And I don't have, see, these are all y equals. I need x equal equations. I need x equal equations. So let's write those 2 equations. So let's work on this one first. So I square root both sides, and I have x equals plus or minus square root of y. And then on the other one, here, cube both sides, x equals y cubed. Okay, so I switched them now. So let's get our brains back into disc or washer. Is this going to be a disc or a washer? It's going to be a washer because one side is not flat and sitting on the axis, right, of rotation. So we have big R and little r. Okay? So little r is measured from the axis of rotation to the underside of the figure, right? Big R is measured from the axis of rotation to the outside of the figure. So let's write little r and big R. So little r, right here, we want to think big minus little, right? This is the x to the 1/3, which is y cubed. Y cubed minus 0. So little r is just y cubed. Big R is here, this distance from the y-axis out here, and that's just square root of y. Okay? So our equation is pi, right, not 2 pi, pi integral, and these are y bounds, and which strangely enough happen to be the same as the x bounds. So that would be really luck, right? Really lucky for us that we couldn't mess that up. 0 to 1 of big R squared, so the square root of y squared minus little r squared dy. We put that in our calculator, and we get 1.12199, which is 1.122. Same exact thing, done two different ways. Hopefully that compares and contrasts the two versions right next to each other. Okay? Are we okay with that? All right.